Okay, so I was saying for a reaction to happen under the collision model, one, the reactants should collide. And then two, the collision should be in a certain order. Okay, the colliding atoms are not just supposed to be in any order, no. The colliding atoms are supposed to be in a given order. So that order that those are going to have is actually the order that will result in these atoms actually reacting. So we've established those two things, but out of those two things, one of them is very important, and that is the minimum required energy for a reaction to happen. So that minimum required energy, I told you that is the what? Activation energy. So here is a diagrammatic representation of what happens for a reaction to happen. You have the reactants there. Okay, there is the reactant. This is an intermediate. So this is a transition step here. A transition step is just a step that reactants have to pass through to produce products. So a step which reactants will go through to produce products. Okay.
Daddy.
So you have this. This is a transitional step. Okay, these are reacting, these are breaking up, a transitional step. Now, the activation energy is the energy that is going to make these particular reactants pass through the transitional step. That energy that is required to pass through the transitional step is the only energy that is used for a reaction to happen. Okay, and then you're going to have products there. So like I said earlier, the reacting atoms should orient themselves in a certain manner. So if you can check, these two are producing that product there, and then this is remaining like that. But if say this on top here was to stand upright like that, such that this is what is colliding with a blue ball there, there will be no reaction. Because in that particular order, these two are not going to give you these products. So such kind of collisions are not going to result into any reaction. So the reactants should orient themselves in a certain order for a reaction to happen, okay? And the energy that is required to pass through the transitional step is the activation energy, a very, very important energy that you have to actually know and compute. Now, this activation energy is computed you have, okay, so here it's molecular orientation is required for a reaction to happen. Okay, so whatever they're trying to talk about here, I've actually talked about. So when atoms are colliding, when they collide in this manner, okay, when they collide in this manner, look at what is happening. They collide, this is the product. Still the same things that you had. But when they do this collision, you will get that. So for a reaction to happen, certain collisions should be in place. Atoms should just not collide anyhow. They should collide in a certain order. If that happens, then these particular atoms are going to produce the required products, okay? And then the activation energy is actually studied using the Arrhenius equation, which you should know. Most people prefer knowing this one for the Arrhenius equation for calculation of the activation energy, but I personally advise you master this one instead, because you can easily derive this from this, then you can that to this. Okay, so you are better off knowing this one than knowing that one. If they ask you to find the equilibrium constant K, the equilibrium constant K can easily be found. The ln of K is equals to the negative of activation energy 1 over T. The time in Kelvin is equals to the ln of A. This is easy to work with, because for you to find that one, you have to do the antilene of this. But for you to actually calculate for anyone, maybe the activation energy from this one, you will need to do the ln of this, which you may forget how to write, to run it from the logarithm, and therefore it might give you a challenge when it comes to calculation. So I personally advise you master this one instead. So equation 12 is a linear equation in the type y is equals to mx plus b. This one, this is y, this is m, this is x, and this is b. So the Arrhenius equation is also the equation of a straight line, and therefore you can use linear regression to actually solve this particular question, because you already know what is presented by what. So this is the equation you're going to use when you are looking at one reactant at a certain condition. Now, activation energy is affected by temperature. The temperature should be constant. Once you change the temperature, the equilibrium constant changes. So you need this equation when you are comparing, when you are looking at how a reaction is going to happen. But when you are comparing a reaction at two different temperatures, when you are comparing a reaction at two different temperatures, what you are actually going to do is compare them using a combined or a modified form of the Arrhenius equation. And the modified form of the Arrhenius equation is this one here. So K is temperature dependent. That is why at a given temperature, the way the reaction is going to happen is going to be different with how it will happen at another temperature. So when you are comparing at two different temperatures, this is the modified form of the Arrhenius equation that you're going to use. K2 is for the second, K1 is for the first, and T1 is for the first, and T2 is for the second. So the equation, when you're comparing at two different temperatures, becomes ln K2 over K is equals to activation energy over R1 over T1 minus 1 over T2. This equation you use when you're comparing them at two different temperatures. And this equation is quick and fast and straight to the point. But one thing you have to remember here is that the units for your temperature should be Kelvin all the time. All right. So I think this should mark the overall end to what we've learned. All we have remained with is so a catalyst does not affect the rate constant. Questions normally on the catalyst under this topic, unless otherwise maybe in a quiz or something they won't ask you such. Highly unlikely, homogeneous catalyst, heterogeneous catalyst and stuff. Simple stuff there. So a homogeneous catalyst is a catalyst that is in the same state as your reactants, and a heterogeneous catalyst is a catalyst that is in a different state than your reactants. So I think basically that is what you just need to know about catalysts. And one other common thing that has been known for a long time is that catalysts do what? Speed up a given chemical reaction. In this case, we're not looking at how the reaction is going to be speed up because you already know. So the thing they'll probably just ask you is to differentiate between a homogeneous catalyst and a heterogeneous catalyst. So this is all looking at the enzymes, how enzymes reduce the activation energy. Okay, so enzymes are going to reduce the activation energy by introducing new smaller routes that use small amounts of energy than the overall. So let me just go to something here. How do catalysts reduce the required activation energy? So what catalysts do is that catalysts will make alternative routes that have lower energies than the required activation energy for a reaction to happen. So they will introduce other smaller steps that are going to require less amount of energy to get to them than the initial transitional step. So a catalyst will introduce other smaller steps for other smaller transitional steps for a reaction to happen. So by so doing, they reduce the activation energy of a given reaction. So that is how catalysts are going to work. So like this, you're going to have a catalyst substrate, and then a catalyst substrate intermediate, then an enzyme substrate intermediate gives you an enzyme and the product. So this enzyme substrate thing here, this enzyme substrate you're having here is actually a step that has lesser amount of energy, and like just breaking these two up, the breaking of the substrate directly to the product. So this is how catalysts reduce the rate of a given reaction. Unless you have questions on your side, this is just the summary, the whole summary of kinetics. Now, any questions that you have, any clarities that you will need on kinetics before we start looking at how questions may be brought and how they can be answered. Okay, so you guys are quiet. Anyway, today we end here. We are finished. You can go through your notes that you learned, that were given to you by your lecturers. You can try to read through the textbook. This is zoomed up. You can go through the textbook and just find where, so this is on chapter 12. You're going to find this topic on chapter 12. Try to go through, try to read through. Tomorrow when we meet, we will actually start looking at tutorial sheet questions, and probably we finish the tutorial sheet questions, and then from there we go to how questions are brought in a test or an exam. So we're going to look at 1 or 2 questions in an exam paper, and then we go to a new topic, and probably we will go to either nuclear or organic. Okay, I personally would say we do some organic before we come to nuclear, because nuclear is a bit easier and straightforward, and organic is what you're doing now. And unfortunately, you've already been tested by giving you a quiz on the some topic. We would have been in a better position to answer had we done some organic. So what we're going to do is, in case there's a quiz coming or something, for you to be ready for that one, we will do organic, the whole course that you're supposed to learn. We'll look at that one up to the end, whether or not you finished with your lecturer, and then we try to look at how questions can be brought and stuff. And then we get back to nuclear chemistry and start revising other topics as well. So we meet tomorrow, same time, 18:30. Clear?